Hey y'all, welcome back. In our last unit, we talked all about exponential functions, and in this unit 8, we're going to be talking about logarithmic functions. But before we get into those new types of functions, we're taking a little stop along the way, and in this one lesson talking about inverse functions, because as we saw in class, the logarithmic function is the inverse of an exponential function. So here we're just talking a little bit about inverse functions so that you have a better understanding of the relationship between logarithmic and exponential functions. So this first section is asking us about points that would have to lie on the line, or not necessarily a line, but on the curve for the inverse of f. So we're given a table of points on f of x and really no indication of what kind of function this is other than the fact that it is a function. So all you need to know to be able to answer these questions is that the domain and range of an inverse are swapped from what they originally were from the original function. So in other words, if I have a coordinate 1, -3 on the original function, then that means I'm guaranteed a point -3, 1 on the inverse. Let's put it like that. Okay, and the same thing is going to go for all of these points where the x and the y are basically just swapped. So if x is 3, then y is -2. Notice I'm just taking the points from the original table and reversing the x and y, and that's basically what an inverse is. The third point, since there's a coordinate 5, 1 on the original function, we know that 1, 5 will be on the inverse. Similarly, if 6, 4 is on the original function, then 4, 6 must be on the inverse. Number 2 is basically the same question, so we'll just copy and paste our answers over here. The only thing we really need to make sure to change is going to be the values here, but it's going to be set up very similarly. So if -5, 7 is a point on the original function, then 7, -5 is going to be on the inverse. Similarly, if -6, -8 is on the original function, then -8, -6 is on the on the inverse function. 1, -2 on the original means -2, 1 is on the inverse. And finally, if 10, 3 is on the original function, then 3, 10 must be on the inverse. So really all I did here was just take this table and just swap my values for x and y, and that's really all there is to an inverse. It's just the domain and range have been reversed. So the function rule for the inverse is really the opposite of what it was for the original function. So down here we've got really just some basic linear functions, and we're asked to find the inverse. So the goal to find the inverse is to swap x and y and then solve for y. So we'll do that for really all these problems here. And all these are going to be worked pretty much the same way. The first thing we want to do is swap x and y. So we have x equals 3 times y plus 2. Then we need to subtract 2 from both sides, so we get x minus 2 equals 3y. And finally, divide everything by 3. So y is going to equal 1/3 x minus 2/3. I just divided both of these terms by 3. And so, yeah, there's the inverse. This is the inverse of the original function. And just to use this new notation, I'm going to write this as f inverse. So we'll have this f have this little -1, which indicates that we're talking about the inverse of the original function of x equals 1/3 x minus 2/3. Now these functions weren't actually called, what happened there? Weren't actually called f. So really, the fact that I'm calling it inverse of f is a little misleading because this original function was not called f. It's just called y. So I'm thinking that maybe what we should do here is just call this the inverse of y. And then not even bring f into the equation here. So basically what this is saying is that 1/3 x minus 2/3 is the inverse of this function y. Now, all of these are going to be solved basically the same way, so I'm going to just kind of copy and paste the work here and just talk through how you would do it. So number 4, we would start by swapping the x and y, and the rest of the equation should stay the same. Then I'm going to add 7 to both sides, and then I'm going to divide everything by -5, so that the inverse of y is negative 1/5 x minus 7/5. And yeah, I think I'll maybe not copy and paste for the rest of these, just because I want to make sure that it's very obvious what I'm doing. Okay, number 5. First, just like with the other two, we're going to swap x and y. So we get x equals 12 times y minus 3. Then we want to add 3 to both sides. So x plus 3 equals 12y. Next, we're going to divide everything by 12, and that is what's going to give us our inverse here. So our inverse will be 1/12 x plus 3/12. Now this 3/12, we can reduce that, but I just wanted to throw it out there just so you can kind of see what's going to happen here and see how I get from this step to this step. 3/12 is going to reduce to 1/4. Number 6, we can subtract 16 from both sides, but first we need to swap x and y. So x equals negative 8y plus 16. But then, yeah, we're going to subtract 16 from both sides and finish this off by dividing both sides by negative 8. So the inverse of y is negative 1/8 x plus 16 over 8, which reduces to 2. Number 7, we'll swap x and y. X equals 2/3 y minus 5. Then we'll add 5 to both sides. So 5x equals 2/3 y. Oh, I'm sorry, not 5x, x plus 5. I was looking at that thinking that doesn't look right. But yeah, so now we could do this in 2 steps or 1. Really, we just want to divide both sides by 2/3, but we can achieve the same goal by multiplying both sides by 3/2. So if I multiply both sides by 3/2, that's going to isolate my y for me. My new inverse is going to be 3/2 x plus 5 times 3 would be 15/2. So in other words, if you wanted to do this using 2 steps, you could multiply everything by 3 and then divide by 2, and you'll end up in the same place. Number 8, swapping x and y gives me x equals negative 3/4 y plus 5. Then we're going to subtract 5 from both sides, giving me x minus 5 equals negative 3/4 x. I'm sorry, negative 3/4 y. Now I want to divide both sides by negative 3/4, but I can, just like in number 7, do this a little easier if I multiply both sides by negative 4/3. So the inverse of y will be negative 4/3 x, and then plus 5 times 4 is going to be 20/3. Start with number 9. It's more the same, really. Let's do number 9 here. We'll start by subtracting, oh no, I'm sorry. First we need to swap x and y. Almost missed that. Then I'm going to subtract 10 from both sides. Now I've already explained this next step on the past couple of problems, so I'm just going to jump straight to it here. I'm going to multiply both sides by negative 8/5. So my inverse here is going to be negative 8/5 x, negative times a negative is positive, 80 over 5. 10 times 8 would be 80. Now this does reduce. 80 over 5 reduces to 16. And hold up, what is this 8 over 8 business? That should be 8 over 5. Little typo there, no big deal. All right, number 10. We'll swap x and y, so we get x equals 1/2 y plus 8. And then we want to subtract 8 from both sides, so x minus 8 equals 1/2 y. Now to solve for y, I want to multiply both sides by 2. So my inverse is going to be 2x minus 16. Now with number 11, notice here we've got a square. We got quadratic here we're trying to invert. Now that just means that our inverse will not be a function, unfortunately. Okay, so we could still come up with the inverse for y here, but it's not going to be a function. And so we'll have like a plus or minus business. You'll see why that happens. But yeah, so let's just go ahead and get to work here. So if I swap x and y here, I get x equals y squared plus 5. Then I want to subtract 5 from both sides. And then this is how I'm going to isolate my y and get my inverse. I need to take the square root of both sides. But anytime you take the square root of both sides of an equation, you do have to include a plus or minus. And this is why the inverse is not a function, because it does require two different equations, and you'll get two different outputs for a given input. And really the inverse here is going to be like a sideways parabola. So yeah, so we get the square root of x minus 5. The positive piece of this will be the top half of the parabola, and the negative piece will be the bottom half of the parabola, and that's why you need both of these pieces to make the full inverse. But note that this inverse is not a function, and that's because we have this plus or minus business going on. Number 12, very similar problem. We'll start by swapping x and y. So x equals y squared minus 4. Then we'll add 4 to both sides. X plus 4 equals y squared. And then to isolate the y and get our inverse here, we're going to take the square root of both sides, but just like with number 11, we do need a plus or minus. So plus or minus the square root of x plus 4. Number 13 has the x plus 3 inside of the square. So let's start by just rewriting it. But what we're going to have to do on this one is actually take the square root before we get rid of this plus 3. So, yeah, we've got y plus 3 equals the plus or minus the square root of x. Then we'll subtract 3 on both sides, and that's going to give us our final answer here, our inverse, which is negative 3 plus or minus square root of x. Now you might be wondering at this point, like, well, at what point does y become y inverse? Really, it should be as soon as you invert. So like all along here, this y is really the inverse of y. But it gets a little tedious to write this over and over again, which is why I just kind of slap it on at the end. So number 14, we'll solve just like number 13, starting with swapping x and y. Now we'll need to take the square root of both sides. So that's going to give me y minus 6 equals plus or minus root x. And then adding 6 to both sides is going to give me 6 plus or minus root x. And that's how you find inverses. You basically just swap for x and y and then try to isolate y. This next section is kind of like the first section, but really asking more pointed questions about very specific values. So I've got this table for x and f of x. I don't have a table for the inverse, but if you recall back when we started this assignment, we said that the inverse was just the original table, but with the x and the y reversed. So we'll just kind of keep that in mind when we get to these inverse problems. So f of 3, I'm going to be looking for where x is 3. So this is my x. So one way of thinking about this is that f of x equals y, or yeah. Okay, so we got our x and our y. And then for my inverse, f inverse of x is going to equal x. So I guess one way to think about this is f inverse of y equals x. Okay. So hopefully this will kind of help you figure out like what values you should be looking for. Okay, so f of 3. So we're going to look for where x is 3 and report back the y value, which is -1. So this thing equals -1. F of 1, find where x is 1, and f of 1 is 5. So f of 1 equals 5. These first three should be pretty straightforward. You're just identifying the y value that's associated with the given x value. F of 5 is, let's see, when x is 5, f of 5 is 0. So f of 5 equals 0. Now when you're trying to evaluate the inverse and you're given the original functions table, you're just going to be locating the y and then reporting back the x. So you're kind of doing the opposite of what we did up here. So if I want to know what's f inverse of 3, that means I want to find the y coordinate of 3, which is over here, and report back the x, which is 6. F inverse of 5, well, if we find 5 down here in the y row, we can report back the x, which is 1. And then finally, f inverse of 0, we are actually going to get 2 values here. Notice there are 2 y values that are 0, so the outputs will be either 0 or 5, which tells me that the inverse actually is not a function. So we can say either 0 or 5. Okay, that took a little while longer for me to get in there. Okay, that's number 20. And that brings us to our final page here. The graph of function f is shown below. Find the following. So f of 0 is just going to be this point right up here. Okay, so f of 0 is b. Just looking at this one. So f of 0 is b. F of what is 0? Well, f of a is 0. Right, we can see when x is a, then the y value is 0. So f of a is 0. Now for the inverse, we're basically just going to be reversing these points. So we're going to look to see when is the y 0 and report back the x value. And we can see that's when x is a. So really like 23 is just the inverted version of 22. And similarly 24 is the inverted version of 21. It's saying f inverse of what is 0. So in other words, how do I want to say this? What y value is associated with an x value of 0? And that would be b. It's kind of hard to put the inverse into words. All right, we got our last section down here. It says graph the inverse for each function below and put your answer on the same graph. So we don't actually have to find the equation. We're just going to sketch this out. And being that I'm using a mouse to do this, it's not going to be perfect, but we'll try to do the best we can. These inverses are going to be reflections over the line y equals x. So it could be helpful to just draw like a I'm doing it in pink here, but you might also consider drawing like a dotted line here, just so you can kind of see that the symmetry is over this line. And it's going to be true for all of these functions. That's just how inverses work. They're always reflections. Their graphs, I should say, are always reflections over the line y equals x. So as I plot points to try to graph the inverse, I'm really just looking for points that are on the original function, and then just reversing the x and y. So like on number 25, I've got this point at -2, 3. Well, that means the inverse has to have a point at 3, -2. So I'm going to plot a point right here. Similarly, we've got a point at -1, 0. That means we have a point at 0, -1. We've got a point at 0, -1, which means the inverse has a point at -1, 0. Hopefully you can start to see the graph come into view here. The original function has a point at 1, 0, which means the inverse has one at 0, 1. And just to really finish this off, we've got a point at 2, 3, so the inverse should have a point at 3, 2. And you can see this sideways parabola starting to become generated. And so I'm going to do my best here to do this in one smooth curve, but, be nice. See if we can do this. Wait, why is it drawn and dotted? What's going on here? Let's try that again. Well, it's not perfect, but hopefully you get the idea. And you can see that if you were to fold this graph along the y equals x line, that these two graphs would match up with each other. Okay, number 26, same kind of idea here. We've got a point at 0, 0, so we know for sure that we've got this point on the inverse. We also have a point at -1, 1, so the inverse should have a point at 1, -1. And the same thing's true for this point over here, which is at 1, -1. The inverse will have one at -1, 1. You might be thinking, what is going on with this one? Well, what's going on is the graph is going to look something like this. There you go. Number 27 is just a line, so we're just going to pick some points to make this happen. We've got a point at 2, 2, so that is also going to be on the inverse. We've got a point at 4, 1, which means 1, 4 is on the inverse. And we've got a point at 0, 3, so 3, 0 is on the inverse, and now we've got enough points to really draw this line. That is pretty bad, but let's see if we can make that a little bit more accurate here. There you go. And finally, our last problem here is number 28. We're going to have a point at the origin, a point at 1, 1. This one's at 4, 2, so that means the inverse has one at 2, 4. And that should be enough for us to get a decent sketch going here, which is going to look something like this. Up. Just overshot it, just barely. Come on, come on, come on. There we go. All right, that's close enough, I think. And that about wraps it up for tonight's homework. As always, please reach out if you have any questions. But other than that, thanks for watching, and y'all have a great day.